So today we're going to talk about forces. So first of all, we'll talk about contact forces. So these forces are forces which occur when objects are in contact. They are of an electromagnetic nature due to the bonds between the atoms and the molecules. So if you imagine anything pushing on another object, the pushing force is due to the electromagnetic force between the atoms of the two solid objects. So what we want to do with these is we want to resolve these forces into components. The tangential, so for example, that might be friction, might be applied force, and the normal force. So another force is gravitation. There's always a force of attraction between two objects. This force is F equals G m1 m2 over r squared, where m1 and m2 are the masses of objects 1 and 2, r is the radius or the distance between the two objects, and g is the universal gravitational constant, which is 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. Force of gravity is equal to mass times acceleration, or mass times the acceleration of gravity. So just using that above equation, we can see that the acceleration due to gravity is that universal gravitational constant times the mass over the radius squared. Just a note as well, the inertial reference frame is a reference frame that is not accelerating. So for example, this could be Earth. If you're measuring two things on Earth, relatively, Earth is not accelerating, even though, of course, it is accelerating in space. Relative to whatever you're measuring on Earth, it is not accelerating. Spring force is another force. So usually spring forces are discussed in terms of ideal springs, which are massless and they obey Hooke's law. So LO is, or L sub O is the resting length of the spring, and S is the displacement or stretch or compression of stretch or compression relative to the resting length. And the magnitude, which comes from Hooke's law, is force of the spring is equal to Ks, where K is the spring constant, in newtons per meter or pounds per foot. Tension is another force. So this has to do with ropes and is usually discussed in terms of an ideal rope, which is massless and inextensible. And the tension directed along the rope is directed along the rope and away from the point of contact with the object. Just a note, it's pretty easy to remember. Tension in non-rigid ropes can pull, not push. So if you have a rope which is non-rigid, you can pull a wagon along, but you cannot push it, for example. An ideal pulley similarly is massless, and it changes the direction but not the magnitude of the tensile force. So an ideal pulley, we don't have to worry about inertia or anything like that. So for a system of particles, these particles may or may not be connected. External forces are any forces that are exerted on the system from outside, and they affect the system as a whole. Internal forces are forces between particles within the system. So again, that comes back to those electromagnetic forces holding the particles or the atoms together. So looking at internal forces, Newton's third law, in which forces come in pairs equal and opposite, applies. So the sum of internal forces is 0, and the internal forces can affect the motion of particles within the system, but they do not affect the motion of the system as a whole. So just a general procedure for any forces, and we'll get into this a bit more with friction, but we want to draw a free body diagram, a kinetic diagram, for each relevant object, including any external forces acting on the object. And then we want to use the diagrams and Newton's second law, so F equals ma, to generate equations of motion. With this, we'll resolve the forces into components, x and y, or normal tangential, and then we'll write an equation, F net equals ma for each component. And we want to use all the tools of kinematics to solve the problem. So equations of kinematics with constant and variable acceleration. Sometimes we need to use these. Sometimes it's simple enough that we don't need to use them, and we can just use simpler equations. So for a video example, it's more conceptual. We're looking at 4 blocks, A, B, C, and D, which lay on a frictionless tabletop. A force is applied to block A, and just determine the acceleration of the blocks. assuming they don't separate in terms of masses of A, B, C, and D, and so on. So, and then there's an extra example to do with the spring force, but that is will be linked in the description. So for this example, first I'm going to draw a diagram. So we have block A here, we have block B here, C, and D. So they don't need to be the same size or the same mass or anything. And we have a force acting on it. So first thing we want to do is draw the free body diagrams and kinetic body diagrams. So for A, the free body diagram will look something like this. So actually, I'll start. We have the applied force going this way. And then we have the normal force, which is pushing back, which is opposite because the forces are equal and opposite. So this is, in fact, the force of B, which is pushing onto A, resisting this force applied. So we can call that the normal of BA, B onto A. There we go. And then, of course, we have gravity, which is M A, so mass of A times gravity, and the normal force. So normal force of the surface onto A. And this equates into an overall force in this kinetic body diagram of mass of A times acceleration of the force. Okay, and then we'll just do B. So B is very similar. So we have, instead of the force, we have the normal force of A acting on B. So that force here gets transferred through the normal force of A. So force gets transferred and the normal force of A onto B. So then we can simply write normal of A onto B. So that force there. Of course, as we saw here, equal and opposite. So there's also the normal force of B onto A, which is resisting that motion. And similarly, normal force of the surface onto B and the normal force of, the gravitational force on B. And that is equal to, similarly, MB of the acceleration. So force equals MA. This is just mass of B times the acceleration of that force. All right, then we'll go on to C. So C is essentially the same as B, except with slightly different subscripts. So we have the normal force of B onto C. That's C onto B, rather. Hang on. Nope, that's B onto C, sorry. And then this is the normal force of B onto C. Okay, yes. So this is the force of C acting on B, and this is the force of B acting on C. And then we have mass of C times gravity, the normal force, surface onto C, which is equal to So the mass, the gravitational force and the normal force will cancel out, and then these two forces don't quite cancel. So if you take this force away from this force, since there's a net force going to the right, then we'll have our kinetic body diagram with the net force going to the right, which will be mca. And then finally for D, we'll have the normal force. So normal force of C onto D. Sorry, just found another mistake. Can't seem to get this one right. Okay, so this would be C onto B and B onto C. Okay, there we go. Anyhow, and then again, those, so gravity and the normal force of the surface. But there is no force counteracting the normal force of C onto D. So that leaves us with this force here, which is mdA. So then we want our equations. So we're going to use these free body diagrams and kinetic body diagrams to create some equations. So for A, we have the force minus the normal force of B onto A equals MAA. So that's simply what we have here. So that's this equation is essentially a representation of this. So force minus normal force. So the force minus this normal force is equal to this force. Okay. Similarly, for B, we have NAB, so the normal force of A onto B minus the normal force of C onto B is equal to mass of B times acceleration. C is very similar. NBC minus NDC equals MCA. And similarly for D, we have NDC is equal to mass of D times acceleration. So again, because we don't have that counteractive force here, it's just that force going to the right. So just a note that A is equal for all of them, so the acceleration is equal for all, and so the normal forces are all equal. I'm sorry. Not quite. But, so for example, normal force B onto A is equal to A onto B because of Newton's third law of the reaction forces. So that means that we can have our third step, which is solving the problem. So we have force equals, and then since acceleration is the same, let's say ma plus mb plus mc plus md times the acceleration, and that just comes from up here. So we have MAA, MBA, MBC, MCA, MDA. So all those accelerations times the masses. And that makes conceptual sense as well because they don't come apart. So acceleration is the same, and the force, that masses add up. So that's just a conceptual example for finding an equation of force. And I believe that has, so we want to find the acceleration. So then acceleration is equal to ma plus m, force over ma plus mp plus mc plus md. So it's equal to the force over the sum of the masses. So this makes conceptual sense. Pretty simple example, but just want to go through it to show you all the steps. Thank you again to Loom and Google Keep, and as well to my professors, and I hope to see you again soon, and I hope this helped.